Picture a fully loaded cargo ship moving across the open ocean. These are mountains of steel carrying thousands of tons of goods, moving with immense forward momentum. You might expect a vessel this massive to rely on complex side thrusters or independent engines for every turn, but at cruising speeds, those systems remain idle. Instead, the entire steering system relies on a single component positioned directly behind the ship's propeller, the rudder. These steel plates house a reinforced internal frame designed specifically to channel massive amounts of water pressure. Small design errors can disrupt the flow of water around the stern, potentially making the ship sluggish or unresponsive during critical maneuvers in narrow shipping lanes. This component holds the balance of the entire ship. It is the vessel's primary point of control and its most significant structural priority. Long before anyone fires up a welding torch, the rudder is born in a purely digital environment. Engineers map out the foundational blueprint using specialized 3D software. They sculpt the exact hydrodynamic shape and calculate the necessary curvature of the steel. This diagram shows a 3D wireframe of a rudder struck by water flow vectors, representing hydrodynamic load, the crushing force ocean currents exert on submerged metal. To ensure structural integrity, simulations test against extreme water flow and varying turning angles. Finally, engineers calculate internal weight distribution, identifying specific stress points prone to fatigue. Validating the model against these digital scenarios helps engineers identify structural weaknesses before the first piece of steel is even ordered. Once the blueprint is verified, the process moves out of the lab and into the heavy industrial shipyard. Here, workers take enormous steel plates and use high-power cutting machines to match the dimensions set by the digital design. The strength of the rudder comes from the internal support frames being integrated into the shell, forming a dense steel skeleton. Intensive welding transforms separate plates into a single, rigid structure, capable of absorbing the lateral force required to turn a cargo ship. The exterior is ground down to a smooth finish to maintain laminar flow, which reduces drag as the vessel moves through the water. Throughout the build, inspectors examine every weld and surface to ensure no microscopic weak points remain in the structure. The build process represents a direct translation of the digital 3D model into thousands of tons of industrial-grade steel. Before it can be deployed, the completed rudder faces a final series of physical tests to prove it can survive decades of ocean pressure. Engineers apply simulated physical pressure directly onto the steel to verify that the internal framing handles the maximum expected stress. They also conduct water flow tests, ensuring the physical rudder behaves exactly as the hydrodynamic models predicted. Once the structure is verified, a specialized protective coating is applied to the entire exterior surface. Saltwater is highly corrosive to steel, and this coating provides a barrier that prevents the ocean from damaging the rudder over its long service life. Finally, the tested and coated rudder is mounted to the vessel in the dry dock, where it is aligned with the ship's propulsion system. Global maritime trade moves forward because of this engineering chain, which converts basic steel into a precise tool of oceanic control.